Hey everyone, and welcome to This Explainer. Look, whether you're gearing up for the Math Kangaroo, tackling the AMC 8, 10, or 12, or just trying to seriously level up your critical thinking skills, you are absolutely in the right place. Today, we're going to look at what is arguably one of the most indispensable weapons in all of competitive math. We are going to become masters of casework.
All right, here's our game plan for today. First, the power of casework. Then, we'll outline 4 steps to success, conquer some absolute values, dive into advanced competition examples, and finally, go over how to avoid common pitfalls. Section 1. The power of casework. Divide and conquer. We have all been there, right? You turn the page of your test booklet, you read a problem, and you just hit a brick wall. Your brain flatlines. There are just way too many moving parts. So what do you actually do when a math contest problem feels absolutely overwhelming and you literally don't even know where to begin?
Well, the answer is casework. Think of it as a logical tool that breaks a chaotic world down into clean, perfectly manageable regions. By splitting an overwhelming problem into smaller, well-defined cases, you're making sure that every single part is simpler than the whole. You conquer each piece separately, you combine them at the end, and suddenly, that impossible monster of a problem, it's completely defeated.
Section 2. 4 steps to success. Your master strategy.
Okay, let's dive into the actual mental playbook here. Step 1 is to identify your source of uncertainty. You're looking for conditions that change behavior, things like absolute values or maybe even and/odd parities. Step 2, divide the problem into exhaustive and non-overlapping cases. This is critical. Every single possibility must belong to exactly one case. No gaps, no overlaps. Step 3, solve each case independently under its own specific assumptions. And finally, step 4, combine your results. It's that simple.
Section 3. Conquering absolute values, the basic sparring.
Let's look at an equation straight from our source material. The absolute value of 2x plus 3 equals 3 minus x. Now, those absolute value brackets, that's our source of uncertainty. Why? Because the expression inside, 2x plus 3, well, it could naturally be positive, it could be exactly 0, or it could be negative. We honestly can't solve it until we deal with that "it depends" factor. And this perfectly illustrates our strategy. We set up 3 mutually exclusive cases based on that inside expression. Case 1 handles when the inside is strictly greater than 0, which happens when x is greater than negative 1.5. Case 2 is our exact 0 point, right at x equals negative 1.5. And case 3 handles when it's strictly less than 0, meaning x is less than negative 1.5. Notice how these 3 specific cases chop up the entire number line without missing a single spot, and, most importantly, without ever overlapping.
Now, solving these in their own independent bubbles is super important. In case 1, the absolute value doesn't actually do anything, simplifying our equation to x equals 0. But wait, before we celebrate, we have to check our condition. Is 0 actually greater than negative 1.5? Yes, it is. It's valid. Moving to case 2, we end up with 0 equals 4.5. That's obviously false, so no solution there. And in case 3, the absolute value flips the sign, which eventually gives us x equals negative 6. Let's check the condition again. Is negative 6 less than negative 1.5? Yep, valid again. So, by rigorously testing our candidate solutions against the initial rule for each case, we get a really clear result. We combine our valid solutions and boom, we arrive at a final solution set of negative 6 and 0. We trusted an organized system, and it turned what looked like a chaotic equation into a total clear-cut victory.
Let's see how this exact same logic holds up when we level up to inequalities with parameters. Here, we've got 2 absolute values adding up to less than 5. So why do we absolutely need casework here? Because each absolute value changes its behavior at a completely different critical point. Specifically, one flips at x equals 1, and the other flips at x equals negative 2.
Those critical points essentially slice the real number line into 3 zones: x less than negative 2, x between negative 2 and 1, and x greater than or equal to 1. If we fast forward through testing those 3 independent intervals, the structure seamlessly guides us right to our final combined answer. X must be strictly between negative 3 and positive 2.
Section 4. Advanced competition examples, combinatorics, and Diophantine equations.
All right, let's shift gears completely and look at integer equations, also known as Diophantine equations. Say we need to find all integer pairs for xy equals 2x plus 3y. The first thing we do is rearrange and factor it. By cleverly adding 6 to complete the product, we get this beautiful setup: x minus 3 times y minus 2 equals 6. Because we strictly need integer solutions, our natural cases are basically handed to us. We just need to look at the exhaustive list of factor pairs for the number 6.
Look at how cleanly this casework organizes into a table. The number 6 has exactly 8 possible integer factor pairs when you remember to include the negatives. By methodically treating every single pair as its own distinct case, like, say, x minus 3 equals 1 and y minus 2 equals 6, we can directly map out 8 perfect integer coordinate solutions for x and y. There is no chaotic guessing here, just pure, rigorous structure.
Okay, now let's bring this logic over to combinatorics. Here's our final advanced battle. How many 3-digit numbers have an even digit sum? And remember, a leading digit can never be 0. Since the parity, meaning whether the total sum is even or odd, depends on every single digit in the number, we really need a solid anchor point. So we have to split our cases based on the hundreds digit.
So, case 1, the hundreds digit is even. Now, since we can't use 0, that gives us exactly 4 choices, 2, 4, 6, or 8. To keep the total sum even, the remaining 2 digits must also sum to an even number. When you calculate those specific pairs, it gives us 50 combinations. Multiply that by our 400s choices, and we've got 200 numbers. Now for case 2, the hundreds digit is odd. That gives us 5 choices. To balance it out, the remaining digits must now sum to an odd number. That's another 50 combinations, multiplied by our 5 odd choices, totaling 250 numbers.
Finally, we combine our 2 isolated, perfectly non-overlapping cases. 200 plus 250 gives us an incredibly satisfying final count of exactly 450. Once again, structured counting beats chaotic guessing every single time.
Section 5. Avoiding common pitfalls, traps to watch out for.
First major trap: overlapping cases. If your cases accidentally bleed into one another, you are going to end up double counting solutions or completely confusing your boundaries. It's a mess. The easiest prevention method is to always use strict inequalities or exact equalities. For example, explicitly separating x is strictly greater than a, x equals a, and x is strictly less than a. Keep your fences up.
Second trap, combining incorrectly. Please do not trip right at the finish line. After you've done all that incredibly hard work solving independent cases, you have to combine your results by taking the union of all valid solutions, never the intersection. You want to gather up everything that worked across all your distinct scenarios into one big, happy solution set. Which leads perfectly to this powerful quote from our source materials: "Embrace casework as an organized, rigorous method." I absolutely love that. Because whenever a problem makes you shrug and think, I guess it depends, you immediately know casework is going to be your greatest ally.
And that leaves us with one final thought. The very next time you sit down for an AMC or Math Kangaroo exam, and you are faced with an absolute beast of a problem, are you ready to turn that chaotic mess into a systematic victory? Seriously, stop guessing. Apply your new playbook, break the problem into clean, manageable regions, and just conquer them one by one. Thanks so much for exploring this explainer with me, and hey, keep practicing.